All right, so now we're recording. Welcome everyone to Zoom for Thought. We're going to have this week Scotty talking to us about grass, man.
Yeah, thanks, Bucky. Yeah, so I'm talking about a project that I worked on back when I was going to school in Montana about the cohomology of real grass munions. So maybe your guys' first question is, why am I talking? Which is a good question to have. Oh, come on. Why am I talking? Okay, great. Why am I talking? So the first reason why I'm talking is because Sam and Baki asked me very, very politely to speak.
Translation, we demanded it aggressively.
Yeah, they asked me incessantly. It didn't stop. So now I'm officially talking. But what I really want to do is I want to introduce you guys to grass munions. And maybe you guys have already seen grass munions before, but just maybe remind you a couple of things about real grass munions. Show you some of their properties, like what's their topological structure, what's their CW structure, what type of space are they, that sort of stuff. And I want to tell you what my collaborator and I worked on for a while, and what questions we answered. And then I also want to tell you why what we did is really cool. So without further ado, I suppose we should get started. So grass munions. Let's first go over the definition maybe. So as a set, the grass munions, GRKN is the set of all k-dimensional subvector spaces of Rn. That's what we're going to consider grass munions today. I know that they sometimes have a more general form, but today we're just considering real grass munions. There's another thing that I'd like to talk about, and that's the Stiefel space. And the Stiefel space is the set of all n by k matrices in Rn, such that the dimension of the column space is k. You could maybe think of this as like GLN, but we're living in like n by k matrices instead of n by n matrices. So a nice thing about grass munions is right now, just what we have is a set. But you and I, we agree that like if we had the set of all lines living in R3, my finger is a line and I'm in R3. And if I move my finger around and I wiggle it a little bit, we would agree that me moving like this line with my finger pointing that way is really close to this line. So we want the topology of this space to be like, we want to capture that. And the same with like the planes in R3. My hand is a plane, I'm in R3. This plane should be close to this plane or this plane or something. So the nice thing is this map from the Stiefel space, where you take a matrix and you take its column space, well, that's a k-dimensional subvector space of Rn. If you take the Stiefel space and you mod out by this, two matrices are same if they have the same column space, you end up with the grass munion. And so we endow the grass munion with the quotient topology here. And this captures the stuff that we wanted. Okay. So now you guys might be saying, okay, Scotty, let's get into the good stuff. Let's talk about the CW structure. We know it's a set. We know that it has a topology. Now, topology, it's a CW complex too. So before we get there, let's talk about this Postset that I really like. So consider the Postset that is n choose k, where you take all injective maps from the set 1 through k into the set 1 through n, where k is less than or equal to n. Another way you could think about this is all cardinality k subsets of the set 1 through n. That's another way you could think about it. So that's a set.
So the second equality, so isn't the first thing like ordered sets, or what am I trying to say?
Yeah.
I don't agree with the second equality.
Okay. That may be. So size k subsets of 1 through n, we could just give those an order, because if it's a k subset, they still have a linear order on them. And if you just order that set that way. So maybe it's not a perfect equality, but
I think
Yeah.
maybe a relevant question is how many elements do you want this set to have? I, of course, being an analyst, can't count. I don't know. So yeah, how many elements do you want it to have? Then maybe we can.
It has
pick
n
one.
choose k elements.
Okay, cool. So
Okay.
maybe we pick the second one maybe in our head.
Yes, I will agree
Okay,
with
cool.
that then. Yeah.
Cool. So now we endow this with a partial order, where if you have a set S that's ordered 1 through k and a set T that's ordered T1 through Tk, S is considered less than or equal to T if Si is less than or equal to Ti for all I. So let's see a couple examples, because right now these are just a bunch of symbols on a page. So let's see some examples. So in set 5, choose 1. This would be the partial order. The set 1 is less than the set 2, is less than the set 3, is less than the set 4, is less than the set 5. Another example would be 4, choose 2. This one is a little bit more interesting. It's not a linear order anymore. The set 1, choose 2, or the set 1, 2 is less than 1, 3, because 1 is less than or equal to 1, and 2 is less than or equal to 3. Same with 2 and 3 and 1 and 4. But notice that 2 and 3 isn't the 2, 3 isn't related to 1, 4, because 2 is bigger than 1, but 3 is less than 4. So there's no relation in between these two. Okay, so we did an example with 1, we did an example with 2. Let's move up to 3. That seems like the next thing to do. So we have the set 6, choose 3. Then we get something like this, where we have all cardinality 3 subsets of 1 through 6, and they're ordered in this way. And it's this nice kind of symmetrical picture. I think it's really pretty. So those are a couple of postsets. And now you're like, okay, why did you tell me about these postsets? I wanted to hear about a CW structure. Well, that's great. We're going to get right there. So before we get there, I want to say a couple little pieces of notation. So if we consider S as a subset of 1 through n, we could consider the space R to the S power, which is a subset of R to the 1 to the n power, which is the same as Rn, if we just consider them as like the basis vectors. We consider this space R to the S to be the span of the usual basis vectors of Rn, where this is basis vector indexed at S1 all the way up through Sk. This is a k-dimensional subvector space of Rn. So we say that the GRKN sub S cell, so this is homomorphic to disk. I'll explain what dimension this disk has in a second. But so V is in GRKN sub S. V is some k-dimensional subvector space of Rn. If the projection of V onto Rs is an isomorphism, and if this S is the maximal such subset that makes this an isomorphism. So I'll do an example here real quick. So if we think of the space GR1, 2, this has a poset 1 is less than or equal to 2. So the two cells that we have are the point, which is a line, who is the span of the vector 1, 0. And there's also all of the other lines that are in R2. And those can be realized as where asterisk is some real number, and 1 just makes it so it's a little bit above. So if you plug in any real number here, notice that this thing is homeomorphic to just the one disk, the open one disk. If we have that right here, I'm going to draw a picture real quick. So that is living inside of this cell right here. But we could also consider any other line in R2, like any other subvector space of R2, one-dimensional subvector space. Well, that intersects this circle at any single point right there. The projection of this line onto R2, which is a subset of R2. This is denoting that R to the S power that I described a little bit earlier. The projection of this line, it can be projected over here isomorphically, or it can be projected down to here isomorphically. But in the Postset 1 to 2, 2 is the maximal such Postset that this line projects onto. So that means that this line lives in the GR 1, 2 subset 2. Everything's still good? Everyone's still with me? Great, rock and roll. And then with this red line down here, I just want to say this one, it doesn't project isomorphically onto the y-axis. It just gets switched down to a point if you project it onto the y-axis. So the maximal one that it projects isomorphically out to is just the x-axis, and that's why it's just a point. So let me clear that real quick. Okay, so that describes like the cells of GR1, 2. And another thing that you could notice that's kind of cool is that GR1, 2 is homeomorphic to a circle from this picture. Great. Okay, so let's do another example. So maybe GR2, 4. So this is the set 4, choose 2. And then right here, this is trying to describe what the cells, like what k-dimensional vector spaces look like in each of these cells. So in the 1, 2 cell, it's just the xy plane. And here, it's the xy plane, but we allow a little bit of motion in the z direction. Here, it's the xw plane or something, and we allow motion in those two. And then here, it's so these stars can be any real number, and they aren't restricted to being like, so this star isn't related to this star isn't related to this star. They can be, each of them can be any real number. And then another thing that you should see is that this one right here has 1 degree of freedom, so it's the 1 cell. This has 2 degrees of freedom, it's the 2 cell. This is also a 2 cell since it has 2 degrees of freedom, and this is a 3 cell. Cool. So then maybe a little bit more explicitly, if I just give you some subset S in n choose k, the dimension of that S is what we say to be Si minus I. And that is also equal to the dimension of that S cell in the CW structure. So now the CW structure is just given by the union of all of these GRKN sub S's. And that gives us our Grassmannian. So now we have some CW structure on it. Okay. Rock and roll. Okay. So we talked about CW complexes, but I want to introduce something a little.
So just a follow-up question on what you had there. So what is the maximum dimension of one of these things? As a combinatorialist, I should be able to answer it immediately, but I don't immediately see what.
Oh, what's the dimension of?
Yeah, of the CW complex. Yeah.
Yeah. So for any Grassmannian, the dimension of GRKN, and also like the dimension of that Grassmannian is equal to k times n minus k.
That's cute.
Yeah. And you can, let me go backwards real quick because I think it's kind of nice to see in this. Okay. I don't want the animations to be making people too sick. So at the end of the day, there are k things that are fixed down here. And this matrix is n by k big. So the places where there are stars is where we have our degrees of freedom. And there's n minus k times k of those stars at the maximal element in our Postset. Cool. Good question. Thank you. Okay. So now let's talk about this thing called the stratified space. So a stratified space is a topological space X that is paracompact in Hausdorff. It has these nice properties, and a poset P, and then a continuous map from X to our poset P. Like, Scotty, how does a poset have a topology? We say that we're going to give this poset the downward closed topology, where a subset of our poset is closed if for every point in that set, all of the elements that are less than or equal to it are also in there. I think when we see a couple more examples, it'll feel better in our bones what that means. Okay, so let's think about this poset. So there's the origin. You can walk north, you can walk east, you can walk west, and then there's northwest, northeast, southwest, and southeast. This is a poset. Things are less than or equal to each other. That works out. And now let's consider R2, but with the map defined as it looks like it should be. If you're in the northeast part of R2, you get sent to northeast in the poset. If you're in the north part of R2, you get sent to north in the poset. If you're sitting at the origin, you get sent to the origin. So then we can feel that the closed sets in the poset are those that match with the closed sets in R2. So this would be a closed subset of our poset. This would also be a closed subset of our poset. It contains everything that's less than. If I look at northeast, well, north is also in there, east is in there, and that's in there. Okay. Here's another poset. 1 is less than 2. That's something that we could have. Oh, but golly gee, we have that Grassmannian that we were talking about before, and that can be stratified by 1 is less than 2, where we say the x-axis gets sent to 1, and everything that's in every other line that isn't the x-axis gets sent to 2. Okay, and now this is back to the poset that I keep talking about. You have n choose k, and then the same way the Grassmannian is stratified by n choose k, by the same CW structure that we gave it before. But now we're realizing the CW structure as a stratified space, where each cell is a stratum that corresponds to an element of our poset. Cool. Everyone still with me? Great. Okay. So when we're talking about these stratified spaces, there's another thing that we could talk about, where links and blowups in there. And in what my collaborator and I did, we worried about these links and blowups. So I want to bring them up before we get to that and what we did. So everything, it's good to just have a lot of examples. So let's go back to this poset, north, south, east, west, that. If we blow up at the origin, it literally is like we plucked a hole out and just blew it out right there at the origin. So you remove the origin, and then you remember all the directions you could have left the origin, just as a smaller little thing right there. So we take the origin out, and we could have gone north, we could have gone northwest, we could have gone west, we could have gone southwest, but we remove the origin, so we just leave that little extra space up there. And then the link is just all of the ways that we could have left 0. The link at 0 of our poset is this thing. And notice that that's just how that's sitting inside of here. And it's also all the ways that we could have left O up here.
Wait, okay, so I'm confused by this definition of blowup. So what is the 0 and what is the 1 thing going on here?
Yes, this is a definition of blowup. It's a little bit cumbersome to write as like a set. because there's these disjoint unions and you're identifying things. So what you do is you kind of basically, you take your poset and you cross it with the poset 0 is less than 1. And then you make a couple identifications and delete some things.
Mm-hmm. Yeah. Okay, cool.
So these are examples for posets, and the idea can be generalized more to these stratified spaces if around our strata that correspond to elements of our poset, we do little collar neighborhoods and make some choices around there. So again, I'm just going to do another example. So let's say we have R2 as the stratified space of this poset. If we blow up R2 at the origin, we pluck out 0, 0, we blow a little bit, and we look at all of the instant tangential directions, not tangential, normal directions that we could have left 0 at. And we end up with a space that looks like this. This would be the blow up at the origin of R2 with this stratification. And you see that it matches up a lot with this picture. This black dot matches up with N0. This gray line matches up with northeast 0. And then all this stuff matches up to this blow up is stratified by the blow up of our poset. I think it's like this really nice deal. And then same thing for the link. All of the ways that we could have left the origin in any direction gets captured by this link right here that's sitting inside of our blow up and matches up with the link that's over here. We could have gone west, we could have gone north, we could have gone all these other directions. Again, it's not, I'm not giving the full super intense, or maybe not super intense, but I'm not trying to push out pullback diagrams right now. I'm just trying to give us a feel of what's going on. Okay. Rock and roll. Okay, so let's think about Grassmannians again. So just in this specific example, we have the Grassmannian stratified by 1 is less than 2. And if we blow up at 1, the GR12 sub 1, what we get is we could have left, we could have gone out in the left, or we could have gone out of the right. So the link of this stratum to this stratum is these 2 points. So we could have immediately exited to the left, or we could have immediately exited to the right. And the blow up is just this entire space right here.
Wait, sorry, that's the link or the blow up, you said?
So yeah, good question. This is the link, just those 2 points right there. And that is the blow up. The blow up at 1. Cool. Okay. One more thing I'd like to talk about is this thing called an exit path. So we just introduced stratified spaces. We talked about links and blowups. Now let's talk about one more thing, which is an exit path. So let's say we have some stratified space, X down to Postset P. An exit path is a continuous map, gamma, which is a path in our space X, such that that path respects the Postset order. So gamma of S less than or equal to T means that if we take it all the way down to the Postset, in the image in the Postset is less than or equal to the other. So now in the same way that we have paths in our space, and we can construct a fundamental groupoid, which is paths up to homotopy. We could similarly create the exit path category, which is our space, and all the morphisms are homotopy classes of exit paths. And that's, we denote that like this, all the exit paths that can be indexed.
Does the homotopy relation need to respect some order as well? Or are we doing just homotopy?
All of the things in the homotopy classes also have to be exit paths.
But if you have two homotopic paths, does there need to be a homotopy that also has some order respecting going on? Or are we just actually talking about regular old homotopies? It's just that we look at exit path beginning and exit path end.
Oh, everything in between must also be.
Yeah, for instance. Oh, okay, cool. Okay, I understand.
Yeah.
Thank you.
So maybe I'll draw a couple of examples and not examples to make it feel a bit better. So I'll draw a couple of good examples. So we could start here. We could walk east for a little while and then walk southwest, and that would be an exit path. Or we could just immediately leave and walk southwest, and that could be an exit path. If we remember our Postset from before, where the higher the dimension of these things there is, the higher in our Postset. Here's something that we can't do. We can't start at the origin, walk northeast, and then come back and sit here. That means that we went higher and then we came back low again. That's bad news bears. That's no good. So the green ones are paths that are good. The red ones are ones that are bad. Like we couldn't start in the southeast and then walk to the west. That's also bad.
And just to clarify, the two green paths you drew are homotopy equivalent in this thing because you can just kind of move.
Yeah, these are homotopy equivalent because we could do a continuous deformation of these, each of which is a homotopy, each of which is an exit path.
Related question.
Yeah.
So if you go through the same points in the Postset, so if two paths go through the same points in the Postset, are they necessarily homotopic?
Not necessarily. No, they're not necessarily homotopic. So is this to say, like, if I have these 2 points in the southwest, are those points? I mean, oh, so there is.
No, I also, right. So I want the exit path. So for instance, they traverse the same points in your Postset. So they go through the same points when you compose. Does that make sense?
Yeah, okay. So if I go from here to there and from here to there, oh, that wouldn't traverse the same points. Oh my gosh. Okay, so the yellow path and the green path, those traverse the same points in the Postset. Those are not homotopic. I should have said homotopic relative to endpoints.
Oh, okay. I see.
Yeah.
Okay.
There is an isomorphism between, like, connecting those 2 points. I'll color it in blue. So this blue path is an isomorphism because it is an exit path. If you go forwards, you would, like, it respects the definition of the morphisms there. And if you go backwards, it also respects that. So you're living in the same spot. So this is an isomorphism. Does that answer your question?
Yes, it does. Thanks.
Tom, you have a question, Tom?
I was just going to say it probably also depends on the homotopy type of each cell, but if I don't think that's a relevant comment anymore because everything is just fine.
Well, Great questions. Thank you, guys. Good. Okay. So the exit path category of a Grossmanian is isomorphic to this thing that's almost n choose k. I put the twiddle on there, not because it's like a very technical thing, but it's almost n choose k. It's like so close. And for an example, the exit path category of Grossmanian of two planes living in R4 is equivalent as categories to this category right here. This is so close to n choose k, the postset. It's not a postset because we have two morphisms going between the cells that we used to only just have one arrow from. But golly, it looks close to n choose k. So that's why I gave it the twiddle. And the reason we do that is because that picture, well, it's not because of the picture, but the picture is indicative of why we do this. So on Grossmanian 1, 2, which is the circle sitting on top of the x-axis, you could have either left from the 1 stratum to the 2 stratum by going to the left, or you could have left by going to the right. And so this exit path category captures like exiting stratum to the left or exiting it to the right. And the thing about Grossmanians is that if you go at codimension 1, like if you're going in codimension 1 strata that are connected in the way that this n choose k twiddle is, you can either go from the left, you could go to the left, or you could go to the right. So when we're thinking about this as a CW complex, this means that when we're trying to understand the boundary maps, we want to understand. I'm going to hold off on what I was just saying right there. Let's save that for a few seconds later. But the biggest thing that I want to emphasize is that we can go to the left or go to the right in all these codimension 1 strata. Cool. Cool. Okay, so moving forward, we want to compute maybe boundary maps between strata and these Grossmanians if we want to compute something like the cohomology or the homology. That's been in general unknown because computing these boundary maps in high dimensions is hard. Trying to understand the degree maps is kind of a tough thing. So let's talk about a couple of things first real quick. So if you think about the link of S less than T, which is what this is referring to is the S stratum links to the T stratum by exiting to the left or exiting to the right. So this link has two connected components. Both connected components are isomorphic to S, and they include into T by either going to the left or going to the right. I have some more pictures to help us feel what this diagram is trying to get to. But so what we want to understand is how that link includes to the S stratum or the S cell of our Grossmanian. And how we do that is by this map rotation to S. And what that's trying to say is we're going to consider exit paths that start at the smallest element of our postset, the minimal element inside of our stratified space. And we're going to just walk methodically until we get to the best spot in our S stratum. And I think that the best spot in our S stratum, in my opinion, is R to the S, because that it feels like just a natural place to choose to represent that stratum. It feels natural for it to be that one. So this map rotation S takes us from the smallest the minimal element, and it walks in a very methodical way through our Grossmanian until it gets to that point. So this map rotation S is this very specific exit path that I'm not going to go into all the details of what it does, but just it's like just a natural, I'm just going to rotate until I get to here and then up to here and then down. I can't move my arm in 4 dimensions, but I hope you can understand that it feels really, it's a nice click when it gets there. So the link describes like how anything in that S stratum can land in the Grossmanian, and you and I should think about how do we get to the best spot in that link, and that best spot is the one that's RS. And the reason that there's 2 connected components is because we can consider that RS to be with 2 possible orientations. There's like the positive orientation and the negative orientation. That's why we have the 2 connected. The 2 connected components are the reason for that. Okay. And then there's another map, which is gam at less than or equal to S, which is a little bit of a thicker link. So before we had a link that was 2 connected components that were homeomorphic to the S stratum. Now, if we thicken them by exactly 1 dimension, that's why we're crossing with the interval 0 to pi. If we thicken them a little bit, now each connected component is homeomorphic to the T stratum, because S and T are codimension 1. So if we thicken each of these connected components by 1 dimension, well, then it's now homeomorphic to something that's 1 dimension bigger. And I think this is a nice picture to maybe see. So this describes the pi map. So if we have the link of a 1-dimensional thing, there's 2 connected components, and that gets mapped to GRKN sub S, where you just send things to where they're supposed to go. This is thinking here about GR1, 2. Maybe, I think if I'm being honest, this is an example for GR1, 3, and this is the 2 less than 3. Oh gosh. Okay. This describes the link of 2 less than 3 inside of there, getting sent to the GRK and 2 stratum. That's what this map is describing. Are you guys still with me?
Wait, is this K you wrote there general K, or is it K equals 1 or?
Oh gosh, yeah. Thank you. Yeah, specifically right now we're talking about GR1, 3.
And also
Right.
just to clarify, in your diagrams, is this like 0 pi? Is that pi the real number pi? Is it the map pi S less T? Is it, what is it?
Yeah, it's a little, the notation is a little bit gnarly. If we could zoom in really close, I think that this would be a boldface pi.
I see,
This is a number.
Yeah.
This one is a map. And I'll try to, whenever the pi or the S and T are there, I'll try to separate them by trying to decorate the one that isn't a number a little bit more.
Yeah, sounds good.
Okay. So that's a toy example of the pi map. And then this is a toy example of the gamma map. So if we thicken each piece a little bit, and then we just include it into the bigger stratum. So I think I said 0 pi here. That I think is a little bit of a typo. I think right here it should be maybe an epsilon. We just thicken it by a little bit and we include it into the higher stratum this way. So We do the link that's at the 0 part and the link that's at the pi part. Like if we walk a little bit to the left or a little bit to the right, this is where we would feel like this link should get sent into. And then there's a map that I'll call maybe like 1/2, which sends each of these points in here to the thickened link, where this red circle gets sent to this red line living inside of this red square. And this blue circle gets sent to this blue line, which is living inside of this blue square. So we could think about this one sending the link s less than t into the thickened link. This 1/2 just is a way for us to feel this link getting sent into here. So the idea here, the reason we have the link and then the thickened link and including the smaller link in there is that we want to compare the orientation, if it's preserved or interchanged or whatnot, if we walk to the left and to the right. So if we're in the S stratum and we walk out to the T stratum to the left, does our orientation, is that preserved or is it reversed? And if we walk out the right way, is that orientation reversed or preserved? What we're trying to do here is we're trying to see how is S glued to T? Because if you walk out to the left and it's glued in a positive direction, and you walk to the right and it's glued in a positive direction, then you loop around T is glued to S twice. And if you walk and the orientation gets reversed and it stays positive in one way, well then T is glued with the degree 0 map to S. Something like that. And that's captured in this disgusting determinant of derivatives of tangent spaces between these links. So yeah, this is, if you pick some L on our link in one of our connected components, well, we can think about the tangent space there, direct sum with some R, like some copy of R. If we're on our link and we get budged a little to the left, that would be if we were on, say the red connected component. And we get budged to the left. Then we want to see, was our orientation preserved when we got budged to the left? And the determinant of this matrix, the sign of it, tells us if our orientation is preserved or reversed. And then if we budge to the right, that'd be maybe the blue connected component does the determinant. Is it positive or negative? Did our budging keep our orientation or reverse it? Okay. That part's a little bit tricky and it's kind of gross to look at, so I'll move forward. So a result that we have is that the degree of a map, since in this chain complex, I haven't described a chain complex yet, but if you, in the same way that we have the chain complex, the cellular chain complex, you can have the stratified space one. And where each of the chain groups are generated by strata of that dimension, the boundary maps are given by a degree map, which comes from the determinant, the sum of this is similar to the local mapping degree result that we find in Hatcher, where if you know the local degree of the preimage of points, you can find out the degree of the map there. So this is akin to that, and here we're using how the determinant of the Jacobian matrix compares. So this point right here describes the angles that we need to plug into the rote map. So this gets plugged into rote, and it sends r to the 1k gets mapped to r to the s. That's what this like data describes. And the 0 says that it gets sent to rs with like going to the left, and the pi represents it going to r to the s to the right. So using this degree map, adding these two together, we get that the boundary map between s and t is given by a formula like this. This doesn't just come out of nowhere. This comes from computing a lot of matrices. Well, I computed a lot of matrices. I was on a computer for like way too long, and the code was really gross and terrible, and I worked through a lot of stuff. And then my collaborator sat down and looked at the patterns that he found in the determinant of those matrices after I like had done all that stuff, and he found this beautiful formula that says, here, the determinants of the matrices you were computing on your laptop when your laptop was screaming and hating you, because there would be some times when I would just let it run for like 24 hours when the dimensions of the Grassmannians were too high in computing these matrices. But he found this beautiful pattern where it's just, if I give you a set S and a set T, it's just -1 to some power of elements of your set S times 2. And it's just, like, this is beautiful. So this is gross. That's gross. I think we all agree that that's like not pretty. But this right here, compared to that this is just stunning. So this made computations of the boundary maps in between the strata a lot easier. And there was this guy back in '79 who got his PhD at the University of British Columbia. It was Jungkind, and he computed the general boundary maps for the Grassmannians. And he computed the homology of Grassmannians up to maybe 7, or something like that. But he just got, our formula matches with what he got back then. So using these, oh man, using these, what my collaborator and I figured out is that using these boundary maps, the singular homology and the homology of the chain complex from the Schubert stratification are isomorphic. So if we use the one with stratified spaces in these links, we get the same homology groups as others. So I want to show you a couple of really good pictures with these boundary maps. So for GR48, this is the Postset structure of it. The red lines represent degree 2 maps between strata. The blue dashed lines represent -2 maps, and the black dotted lines represent 0 maps. So it's just weaving in stuff. But then if we go to GR510, we just removed all of the maps that are degree 0. And you can see that there's all these squares and cubes living inside of this picture. And what Jungkind didn't have in '79 that we had today was a computer. So we could compute all these maps and get pictures like this that showed us these cubes, and then it could make us be like, oh my gosh, there might be a pattern here. We might be able to actually find the homology groups in like a pretty way. And then let's go even further and look at Grassmannian 612 and the maps there. So the red ones are degree 2 maps, the blue ones are degree -2 maps, and all the blank spaces are degree 0 maps. So what my collaborator did is once we started seeing these pictures, he got this wonderful, wonderful result. This is huge. There's an isomorphism of graded R modules or the cohomology of any Grassmannian with any commutative ring R is isomorphic to the direct sum of Vs in the dimension of S, where Vs is given by R. If the number of arrows pointing in to your stratum in that picture is empty, it's equal to 2 if the number of like out arrows and in arrows, if there's only arrows going out, it's the kernel of this map. And if there are arrows going out and in, but the smaller, like the smallest out value is on the arrows going in, then it's the co-kernel. So maybe this is a description of the in and out, but I'll maybe try and show you an example real quick. So let's remember what VS and in and out are. So here in 1, 2, 3, 4, 6, there are no arrows going in, and there are 2 arrows going out. So in and out doesn't equal the empty set, so we're not going to do that. But the minimum of the in and the outs is definitely going to be in the out because there's only arrows going out. So this is in dimension 1, dimension 0, dimension 2. So H1 of GR 5 or 5, 10 is equal to, I'll say it with Z coefficients, is equal to Z, the kernel of Z to Z, the 2 map, which is just equal to Z. Whoa, did I do that right? Yeah, I think I think I get Z mod 2. No, the kernel is 0. I may have tried to rush a little too quick there at the end, but I hope the exciting thing is that there's in arrows and out arrows, and it's this problem that's super easy now to compute. And you just, instead of having to compute derivatives, you just look at n choose k, and you can compute the homology group there. So this is hugely exciting. The 112th cohomology group of GR1530 is equal to Z to the 155th direct sum of Z mod 2 to the 1.2 millionth. So it's wild. That's new. So
That's pretty sweet.
yeah, thank you guys.
Do very nice. All right, everyone, let's thank the speaker. Are there any questions for the speaker? I have a question.
Yeah.
The proof of this infuriatingly nice formula, is it linear algebra? Is it clever linear algebra, or is it like combinatorics, or what's the deal going on there?
I think it's a lot of. I think it was a lot of clever linear algebra. I think
Linear algebra is the best.
is that fair, Eric?
Yeah, I mean, pretty much at the end of the day, it just came down to a bunch of like linear algebra and a little bit of like combinatorial stuff. But yeah, mostly just some linear algebra, I suppose.
Cool.
Which is pretty cool. It's just everything, you know.
Yeah, that's very neat. Any other questions?
I don't know if this makes sense, but would any of this generalize to other kind of like flag varieties, like these techniques?
Yeah, I think that the hope for these stratified spaces is you can have any conically smooth stratified space, and that includes all manifolds with corner, or like you have a lot, like it's a big general thing.
Yeah. So the theorem we proved is that it works for any stratified space whose cells are diffeomorphic to Euclidean space. So like some other examples that would be cool to use this on would be like the orthogonal groups and stuff.
Mm-hmm.
And another good generalization or like direction to go with this is we just computed the additive structure would be to like realize the cup product through this and things
That's what
like
I was
that.
going to ask next, actually.
Does the cup product structure, can you get that out of these spectral sequences usually?
Yeah, I think I thought about this a little bit a while ago, and then I haven't because I've been trying to finish something else up.
Mhm.
But yeah, I think we can realize the cut product structure through this setup. So yeah.
Can this sort of approach work over fields other than R? I guess you sort of answered that, but
R was any ring, right?
R was any ring.
You mean like
you-
the real Grassmannian, so like over complex numbers? or
like
something?
Grassmannian maybe?
Yeah, well, the complex has already been known for a while. And you can actually read off the complex stuff from our sort of real computations, I guess. The boundary maps are going to be, oh, never mind. I'd have to think about that, but
Cool.
you can see the complex structure like through ours, but also the complex has been computed like a while ago, I think.
Awesome. Any other questions or comments?
Can I ask you a question about the pictures that you had?
Yeah.
Were they the Postsets, or I was a little bit confused by what you were showing us.
Yeah. Let me get back there. So those are the Postsets, and they're ordered by like cellular dimension. And the red maps describe the boundary maps in the chain complex, where each of the like cells, so the cells generate the chain groups, and the red and blue lines are representing like the boundary maps between like the chain groups in like different dimensions.
Okay, but this picture is all you need to use your formula, right? So
yeah,
I think the colors and the graph and your.
Sweet. Anything else? All right, let us thank the speaker once more.